Welcome to our next video in the series on condensed matter theory. In this video I want to look at the example of a two-dimensional square lattice with hydrogen atoms on each lattice side, where we make a tight binding model and we will only keep a single s orbital per hydrogen atom. This is very simple, very similar to the previous example where we looked at a one-dimensional tight binding model, but now in two dimensions. And of course our world is not one-dimensional or two-dimensional, but three-dimensional, but I want to show you how we can make that extension. And once you've seen how you can do a two-dimensional system, I hope you will be able to generalize to a three-dimensional system. So we take a square lattice where we have lattice vectors a1 and a2. With that we can generate a reciprocal lattice, which is also square. It's not always the case that the real space and the reciprocal lattice have the same symmetry, but for the simple cubic it definitely is, and we have our reciprocal lattice vectors b1 and b2. So a1 is the vector 1, 0 times a2 is the vector 0, 1 times a, and the same b1 is the vector 2 pi over a times 1, 0. b2 is the vector 2 pi over a times 0, 1. The real space lattice vectors are given by n1a1 plus n2a2. The reciprocal lattice vector space m1b1 plus m2b2, where n1, n2, m1 and m2 are integers. We will have a look at nearest neighbor hopping only, nearest neighbor hopping. And our Hamiltonian is given by a sum over all lattice vectors, epsilon 1s, a dagger r, ar, so that's the on-site energy, plus hopping, a dagger r plus a1, ar plus the harmonic conjugated, and we can also hop in the other direction, a dagger r plus a2, ar plus harmonic conjugated. Now we can do a Fourier transform, and very conveniently the a1 and the a2 direction completely decouple from each other. So we can do just a Fourier transform of this Hamiltonian or of this, and you then just have to sum them. So this is in principle 2 times the example we did in one dimension, and we get epsilon 1s plus 2t cos kx times a plus 2t cos ky times a dagger k ak. So we get a cosine dispersion in the x direction and a cosine-like dispersion in the y direction. We can now have a look at the crystal momentum as a function of momentum. But of course, the momentum is now a two-dimensional vector, so in principle this is a three-dimensional plot where you have a surface as a function of kx and ky. That makes for nice plots, but not always for the easiest quantitatively to understand. So what we like to do is to follow a path in k-space through the Brillouin zone. So let's say we start at the point 0, 0. So if you look at the Brillouin zone, then we have here the point 0, 0, here the point 0 pi over a, here the point pi over a 0, and the point pi over a. So that's your Brillouin zone. So the first track that we're going to follow is from here to there. So that's from 0 to pi over a. In this case, ky is 0, which means that is just a constant, and kx is varying in a cosine-like behavior. And we get a dispersion of size 4t. Next, we're going to move from 0 pi over a to pi pi. So let's move in this direction, which is this section here. In this case, kx is constant and ky is changing, again with a cosine-like dispersion. So we're going to move like this, and again giving you a dispersion of 4t. Well, in the last section, let's just move along the diagonal. And now we're going to move from pi over a back to pi over a to 0, 0. And that is then again going to be a cosine-like dispersion. But now both kx and ky simultaneously change in the same fashion, so that in the end gives you a bandwidth of 8 times t. Note that at gamma you start at a minimum, and that is because t is negative, which is what we have derived for the interaction between two s orbitals. We can also look at the densities of states. Now at the zone boundary, your dispersion is flat, but there is only one point pi over a in the full Brillouin zone, so that intensity no longer diverges, but we do have a kink in the energy momentum dispersion. At the point 0 pi, your dispersion is also flat, and here you have this for a whole range of momenta in the other direction, so there the densities of states still diverges, such that we have a densities of states that looks like this. And with that, extending to 3 dimensions would just give you an additional dispersion in the z direction on top of what we have seen here, which allows you for relatively simple extensions. So far for a tight binding model in 2 dimensions. Thank you very much for your attention. We see each other in the next video. Stay healthy.